Good morning, everyone. Welcome to the second day of the community forum. It's good to see you all. I want to say a special greeting to our distance students who have returned to campus to join us for this special week. Thank you for making the effort. We're so glad to have you back. Well, this morning we have something special planned to kick off our day. We're going to be offering reflections on our gratitude and friendship with Sally Thode. Sally has been a mentor and instructor in the MEM program for 10 years and is just about to retire. And we want to take this opportunity to express our love and gratitude for Sally. I will keep my reflections super brief because we have some other folks queued up, but I'll just start by saying I just returned from the Mississippi River expedition with some of our grad students and had the privilege of having Sally join that journey and the opportunity to get to know her better. And first of all, she's just a fantastic human on so many levels. And it was just lovely to spend time in her presence. But it also really affirmed for me that Sally is an incredible mentor. And I really respect her commitment to our students. I knew that before, but seeing Sally after a long day on the river or a long day on the road, sit down to work on revising and providing input for the products that our students are making and doing that at like 11 p.m. Just really shows her care and commitment to seeing our students thrive both in the programs here and beyond. And I know that over the years, I've just received so much positive feedback from the students who have had the privilege of being guided by Sally through the MEM program, of course, and discerning what classes to take and what project to prioritize that would meet their career goals, et cetera. But really, Sally has been providing so much more than that. And we've seen those students really develop as professionals, but also as people and as future leaders. And time and again, we've just heard rave reviews about her mentorship. So Sally, thank you for your high degree of commitment and love and support of our students. We see it and we really, really value you. I'm going to pass this off to a few of our friends from the Clark School. So Courtney, why don't you come up and start us off? If you'll please introduce yourself and your role and then offer a reflection, that would be great.
So my name is Courtney King. Some of you know me. I have been back at Western for a little over a year as staff with the Clark Family School, but previously I was a student in the MS in Ecology program. So kind of wanted to speak a little bit about Sally from someone who I never had any official classes with her, was not my official mentor, but certainly served as a mentor in my life, as I know she has many others. So I wrote, and Sally is a true mentor, someone who takes a personal interest and investment in those around her. As I prepared to graduate, she advised me about opportunities in the government and the notoriously tricky federal application process. Over a year later, when I wasn't sure whether my position at the time was the right one for me, she helped me navigate the culture of a federal agency, reflect and think long-term about my career while connecting me with others who could help too. She has inspired me as a woman in land management, and I know she has inspired many others around her, again, serving as a mentor, whether officially or not. Beyond supporting students as they find their passion, Sally connects with and supports those around her in all areas of their lives. She provided a smiling face on my first day back to Western and has offered myself and others a place to park or a couch to crash on while in the midst of traveling. I've also enjoyed connecting with her about our travels and hikes locally or beyond. And you see a lot of that here. Sally's also one of the foremost public land stewards of the Gunnison Basin, with over 2 decades of experience in the federal government that she's leveraged to aid and inspire students and newcomers to the field. Her lifelong interest and dedication to the land has been exemplified in her involvement in annual Public Lands Day events, and she has all the shirts to prove it. Um, while I hope, Sally, you find time to relax in retirement, I'm sure you'll also be found hitting the trail, pulling cheatgrass around town, and continuing to explore ecosystems and connect with communities around the world.
Thank you so much, Courtney. Pat, would you come join us, please? If you'll introduce yourself and then offer your reflection.
Hi, everybody. Morning. I'm so happy to be here, and I'm also super honored to be able to do this for you, Sally. I was also with Micah on the trip down to the lower Mississippi River, and I've known Sally for almost 3 decades. But I got to spend the most time I ever had with her in the last 3 weeks, and it was just really wonderful. We found ourselves, Sally and I hung out a lot on that trip together and found ourselves in New Orleans, walking around the city, looking for ice cream, actually. And we found ourselves on Bourbon Street, and we realized you can get anything you want on Bourbon Street except ice cream. So it was a good adventure. But anyway, I wanted to ask you to participate in something. So you ready? Give me an S. Give me an A. Give me an L. Give me another L. Give me a Y. What does it spell? Sally. I put together a little thing. I think they call it an agnostic thing. So S. S stands for steady and service oriented. And as I said, I've known Sally for a long time, and she's always been one of the most reliable people I know in my life. She's there as a friend, as a person that always steps up. As Courtney mentioned, she's, even after a 25-year plus career in federal government, she is one of the most reliable, dependable people on every one of the public lands days. And just a very steady, reliable, wonderful person with a service orientation. She and Jess, of course, were very instrumental in helping out with the COVID response, hours and hours and hours of helping our community. So really appreciate that first S. The A is for adventurous and active life. Sally is a very avid hiker. She's a global traveler. She's been to almost every continent. Maybe she has been to every continent. And what I love about the travels that Jess and Sally have taken is that, of course, it's for the adventure and for, just getting to see the world. But every place they go, they always make friends. They always try to improve the community. They always give back. They're so generous. And I know that they've maintained those friendships from around the world for many, many years. So very beautiful. L, I think this might be my favorite one for Sally, and L stands for loyal and loyalty. She's a loyal friend. She's loyal to her work. She's loyal to her partner, and she's loyal to herself and to her own values. And I know one thing that has always been inspiration, encouragement to me is to try to live my life in alignment with my values. And that's something that Sally has just mastered. And I know that that brings a lot of peace and joy in someone's life. So I can also say that Sally is one of the most loyal Bronco fans. And every Sunday during football season, she puts on her orange jersey, and whether they tie or lose, she's still there. So, okay. The other L stands for life changer. And Sally has been, had a really wonderful career, both as 25-year plus career with the BLM, guardian of our precious, beautiful, and sacred public lands. And just so loyal to that cause. As I said, keep doing that after her career. And as Micah mentioned, a 10-year veteran now with the MEM program as a mentor, and just really helping students to take this next step in their life, prepare themselves for what's coming next. And Sally's just been a genius and amazing at being that mentor for people. And the last one, I wasn't finding the best word for this one, but we're going to say yippee. Yippee. And what I meant by this one is that Sally has some hidden talents that maybe some of you don't know about, but for while she was working for the BLM stationed out of Lake City a lot of the time, she had an alter ego that came out at night. And this alter ego is as a performer in the theater. And Sally did this for years and years with the Lake City community. And she danced, she sang, she acted. It's an absolutely amazing thing that she did. And I think it brought her just a huge amount of joy and fun in being part of that. So you never know what's going to come out of Sally. Anyway, Sally, I love you so much. And thank you for everything you've done for our community, for Western, for the world. So thank you.
And lastly, Nate, would you please join us?
Thank you. Morning, everybody. For those of you that do not know me, my name is Nate Gore, and I'm a lecturer in the Environment and Sustainability undergrad program. Before that, I was also an MEM student, and I'm very gracious to have had Sally as my faculty mentor. When Micah opened up the space and asked anyone to come out and share some words, I was very quick to volunteer to share my gratitude for having gotten to know Sally in this very cool role. With that being said, the stories that come to my mind are so overwhelming and just too many to really count. But I do have a couple that, for the sake of brevity, I'll cut down, but I will be very happy to share. Sally, you might not even know this first one, or maybe you do. It'd be funny to hear it from your perspective. But coming to Western and coming to the MEM program was actually kind of a relatively impulse choice of mine. I was at kind of a crossroads in my life, and I saw all the information for the MEM online. It was like, that looks cool. Western Slope looks cool. I've never spent a lot of time down there. Why not? I'll apply. And I did, and I was accepted, but I wasn't really still that committed. I was accepted and I was technically in the program, but it's a little on the fence still. It's a big decision. I never imagined myself as a grad student or going for a master's degree, believe it or not, which is crazy now to think back on. And I remember the first assignment of EMVS 601. It was just an online one-page reflection, and I was late turning it in. And Sally emailed me and was like, hey, are you turning this in? And then I did. I just needed that like one little push from Sally, and I was like, okay, I'm a grad student now. I guess I'm coming. Guess I'm moving in 2 months. And that's crazy to think back and reflect on that now. I don't know if you realize just the gravity of that small gesture in sending me that email, but that was far and away one of the most pivotal decisions of my life to come out here. You know, I fell in love with this relatively slower Western Slope lifestyle. Finishing up the MEM program really helped me build this network that I love. And now I have, on most days, my dream position. This is like such a cool opportunity to be here. And that's really because of you. Just being here has opened me up so many avenues professionally, personally. I also met my fiance here, and I don't think I would have done that if you didn't send me an email and convince me to go to grad school. So thank you for that. Yeah. And that, I think, all just speaks miles to the character of Sally's mentorship. Pat, I love how you said life changer. That also is something immensely that came to my mind as I was thinking of this. I'm also very grateful that even well after I finished the MEM program, Sally and I have been able to keep in touch. We always find a time to go grab a coffee or just hang out every now and then, go walk around every couple months. And I've also been able to get Sally to come guest lecture for a lot of my undergrad classes. So even after your time out of the classroom is really concluded, I've still gotten you in front of about 100 students over the past 2 years, which is super cool. And I've learned so much just from watching you teach in different ways than I normally have. And it reminds me that you don't need a PowerPoint unless you're going to show some awesome pictures. Yeah, so thank you, Sally. Thank you for everything that you've done for me, for all of the other students, for the entire community as a whole, for Western, for our public lands. You've been an inspiration to everyone in this room and really to me. So thank you.
Thank you, Nate. And thank you, everybody, for sharing those reflections. Sally, I promise I won't make you say anything, but would you join me on stage for a round of applause? We want the folks online to be able to see you and appreciate you as well. As a token of our gratitude and congratulations on your retirement, we have some gifts. And I encourage all of you to find Sally at our next break and give hugs and love and gratitude as well. So thanks so much, Sally. Right. Okay, with that, we are off and running. So I would like to invite Jonathan Koop to the stage, who's going to be facilitating our first panel of the day.
All right, thank you. My name is Jonathan Koop. I'm a professor here and the co-director of the MS program in ecology. And I'll just offer another word of congratulations to you, Sally. And one thing that I didn't know about until I watched the slides was how many interesting kinds of food you've eaten and strange animals that you have held. So congratulations on those feats as well. All right, they handed me a whole bunch of papers and things that I'm supposed to coordinate here. But basically, we will, until about 10:30, be enjoying our first panel presentation of the day, which features 4 students, 3 of whom are in the MS program and 1 of whom is a MEM student. The title of the panel is Sagebrush to Subalpine, Shifting Community Dynamics. So will welcome the panelists to come up here and enjoy their chairs, and there'll be a 5-minute presentation about the panel overall. Then each of the panelists will present for 13 minutes, following which there will be 2 minutes for questions, and then there will be a 10-minute chance to ask questions of the entire panel. So that's the general order of things. One caveat is that one of the panelists will be presenting via a video. So we'll try and make that happen effectively. And yeah, if you have questions for the panelists, please check out the QR code and use the Slider app and ask your questions through the app. And then I will do my best to read the questions from one of the things that I'm holding here. So yeah. Welcome our first panelists. Please join us and enjoy a nice comfortable chair on the stage. Curtis Beutler, Jack Betz, Tina Schafer, and via distance, Landon Lemmens. So,
hey everyone. So our panel today is Sagebrush to Subalpine, Shifting Community Dynamics. I'm Curtis. And so our panel today, you'll see presentations that span many different scales of ecological inquiry. We're going to look at population dynamics with Jack's work, which was mainly in a lab, but looking at how sagebrush will change in a future climate. We're going to look at the community scale with Tina's presentation, looking at Gamble oak, which is kind of a shrub, kind of a tree. It's definitely heinous to work in. when it grows thick. So nice job, Tina. Landon's work looks at kind of the tree stand scale, but also kind of the regional scale as he came up with treatment strategies that can be scaled up to the whole region he works in. And then my study looks more at like the landscape scale. And I think that as you guys get to watch these presentations, it'll instill sort of an appreciation for the different scales of ecological inquiry and kind of underscore the importance of each one. So we'll also be looking at a whole array of landscape types today. Landon's work is in Appalachia, so quite a bit lower elevation than we're used to. But then us three looking at the western slope of Colorado here, we will span different elevations more in our local region, with I think Jack's being the lowest, Tina more in the montane zone, and then my work is up in the subalpine. So when I was looking for images of elevational ecotones online, I really like this one because I'm a hydrologist at heart and had to include something about precipitation and rain shadow, and talk about how 80% of our water resources in the state fall on this side of the continental divide, even though 80% of the people live on the eastern side along the Front Range. But we've got the better side, we know that. Yeah.
Landscapes are managed for a variety of reasons, ranging from economic, cultural, recreational, or ecological. And so all of our projects kind of focus on how we manage lands and for what purposes, with Landon's looking at a bug that's detrimental to forests on the east, to the why we're managing our lands for water, the hydrologic cycle, and with climate change, there's drought and fire, and how to manage the land as those things persist on the landscape. Additionally, we all looked at different factors influencing the lands we work on. So there's abiotic factors, land such as the fire, climate, or biotic factors like Landon's, which was a bug.
Lastly, as we're talking about sort of the through line of our projects, we're ecological dynamics sort of sprang to mind. We're going to be touching on some of these in our projects. Succession, sort of the switch, predictable shift from one type to another. Certain replacement events, maybe a extreme fire knocks out all the live seed sources. But just the idea that these systems are in motion, they're not necessarily static, but maybe cyclic or linear in fashion, but they're moving. And the question is, where are they moving to and sort of what that looks like? Biological invasions, as has been mentioned, and that could be an insect or cheatgrass, which we all know very well, coming in, switching up the system. Range shifts. In this photo up on the left, we've got a good shot of the Arctic. We're seeing tree species move up to where it is now warmer and they can thrive a little bit better, whereas in prior years it was too cold, but seeing these poleward and northward range shifts. And I'll talk a little bit more about that in my study. And then changing ecological hydraulic function on a landscape, how water interacts with tree cover, forest types, which is a great segue into our first presenter, Curtis.
Hey, Curtis again. So I'll be presenting my thesis work today for the MS in Ecology program, which is forest composition and structural controls on canopy snow interception. So a little bit about me. I've been digging holes in the snow for quite a long time now, but I like it. And my research really looks at the intersection of snow, water, and ecosystems. This photo on the left is from 2015 when I worked for a research institute at CU. It's anyone's guess what I'm saying there, but probably yelling at an undergrad intern. It happens sometimes. And I've lived in the Gunny Valley for 6 years now. That photo in the middle is from my first winter up here. That's a snow pit at the top of Washington Gulch. And any guesses about how deep that one was? You can just yell it out too. We don't need to like do the phone thing, any of that. 20 feet. That's a little high, but yeah, it was 4.5 meters. So pretty close to 15 feet. It took us like a whole day to dig that one. So when I'm talking about canopy snow interception, we can boil that down to snowy trees. That's what I looked at for the last 2 years. And interception is kind of an aggressive term, but that's how hydrologists think of it. You know, it's really just these trees out living their life, getting snowed on. But if you're a hydrologist, you're angry at those trees. You know, I mean, if you think about it, they're stealing our water, like not letting that snow get to the ground. But why would we want to study snowy trees? Well, we know that worldwide, mountain watersheds are the primary resource for 1 billion people, and they act as water towers where they are able to store water and release it gradually at times of the year where we need that water. But these same watersheds are also signals of climate change. They're changing faster and in different ways than many other ecosystems. In our own backyard here, we've seen a 25% reduction in snow storage. So the ability of these mountain watersheds to act as water towers in the last 60 years. And looking forward, we expect a 35% decline in snowfall by the middle of the century. So thinking about forests globally, we also know that they're at risk of wide-scale change under a future climate. And in the Western US, we're seeing that they're increasingly susceptible to disturbance-driven conversion. And that's a big deal because we have a big spatial overlap of our snow resources in the West and our forests. And some of the primary species that make up that overlap have starkly different successional traits. So under a new climate, we expect the forest makeup to change a lot and dominant species to emerge. In North America, about 20% of our seasonally snow-covered areas are forested. I think that number is actually a little bit low too. But thinking about what some of those successional changes look like, in Colorado, it's been documented for a long time that we can see these big homogeneous lodgepole pine forests be established, but when disturbance comes in, like wildfire or insect mortality, we can see a pretty quick shift to aspen or lodgepole pine becoming the dominant species. So if we know that snow is changing and we know that forests are changing, the logical next step is that their associated ecohydrologic function, basically the interface of the hydrologic cycle with the ecosystem, is changing. And that's especially true for snow-dominated systems. And a big part of this is what we call forest-snow interactions. So basically all the diverse effects that canopies have on the seasonal snowpack. And that's everything from shading the snow, creating a new wind climate, but also the deposition of organic matter on the snow that can cause it to melt much faster. But in my opinion, canopy snow interception is the biggest piece of all of this. It's a first order control that forests exhibit on the snowpack. And we know that the canopy can intercept up to 60% of seasonal snowfall, and up to half of that can be lost to sublimation, where you get in the solid phase snow transitioning to water vapor straight back to the atmosphere. And this is the peak of my artistic endeavors during my time at Western. Or that might not be true. I wrote a haiku for Coop's class, so that might have been the peak. But my basic PowerPoint illustration here is just showing the different forest snow interactions that we expect, and essentially whether that's a negative impact on how much snow gets to the ground, or there's some positive impacts as well. And then on the right is our hypothesized relationship between forest composition and snowpack going into this study. So we've been thinking about how to get as much water as we can out of forests for a long time. Hydrologists can be a little bit greedy in that aspect. We want to clear cut the forest in different ways to see how we can get the most water out of it. We want to build dams and build reservoirs that you have to build bridges across sometimes. But no, but we've been thinking about this concept for a long time. And likewise, we've been thinking about canopy snow interception for a long time as well, studying it directly. And since the 60s, we've seen a variety of ways that we study interception, from cutting off individual branches and weighing how much snow lands on them, to cutting down individual trees and seeing how much snow lands on them, to hanging artificial trees and bombarding them with lasers, which is a recent development. So in this study, we hope to look at interception differences across aspen versus conifer forests, different conifer tree species, vertical structure, so individual canopy geometries, and then horizontal structure, more at the stand scale, how neighboring canopies impact interception. And we also wanted to look across different kinds of weather events. So from cold storms in December all the way to warm storms in March. But if we know that measuring interception is so difficult because it's so variable and intermittent, how are we going to get enough observations to look across all these different groups? Wait for it. I lost the slide. I had a laser slide, but lasers, that's how. Anyway, we're working in the upper Colorado River Basin, a place where water is pretty important, in the East River watershed. And in the East River watershed, all our sites were on Snodgrass Mountain, northwest of Crested Butte. And Snodgrass is super cool because it has this great mix of conifer and aspen forests, which you can see in the different shades of green on the left map. And if you're looking down at Snodgrass Mountain from the ski area, it's easy to tell that geographically it's less complex than a lot of surrounding mountains and high elevation areas. And that's good for us because we need to control for elevation, wind exposure, and aspect if we're going to keep interception variables fairly controlled. And so our method for this was running around after a big snowstorm event with what's called a terrestrial laser scanner, AKA terrestrial LiDAR. And that's a really cool tool because it allows us to collect a lot of data really quickly. And quickly is the most important piece there because basically as soon as snow is in the canopy, it starts to change. And as soon as it becomes sunny or windy, we can start to see that snow fall out of the canopy. We also use drone imagery from Rocky Mountain Biological Lab to do species ID for each of our trees. And then nearby weather stations, the closest of which was only a couple hundred meters from our sites to constrain the individual weather events. And so on the bottom, we can see essentially how we calculated how much snow was in the canopy. We took a snow off point cloud from the LiDAR data, and we're able to combine it with a snow on point cloud and get this merged data set, which allows branches to occupy the same space, but snow to really represent an increase in the tree volume. And in that way, we were able to calculate the snow volume in trees for each study date. The LiDAR data is super cool because it also allows us to accurately quantify forest structure. And that's everything from individual canopy structure, vertical structure, like we talked about, to more stand scale metrics like horizontal structure, and actually a bit in between where we're applying both scales of forest structure to neighboring canopies. And the reason that this was an important goal of our study is that if we had a good idea of how forest structure impacts interception, we could use bigger data sets like aerial LiDAR to expand these observations over a whole watershed and improve hydrologic modeling. So in all, we collected a ton of data, but only across 4 sampling events, which felt like a lot to me, but doesn't sound like a lot. And we had 120 trees across all of our sites that we looked at. which translated to 2 billion LiDAR returns, or 2.5 terabytes of data. We had to write 5,000 lines of code to process that. And I spent at least 2 hours getting the snowmobile unstuck across all the sampling dates, and then at least 5 trips to the physical therapist to fix myself after those snowmobile excursions. So we knew going into this study that aspen trees intercepted less snow than conifer, but just how much we didn't know. So it was cool to quantify that it's actually 10 times less interception that goes on in these aspen forests. And looking at this table on the right, you can see that our conifer forests on individual events prevented as much as 30 centimeters of snow depth from reaching the ground. And when we applied our snow density values from local weather stations, that translates to up to 3 centimeters of SWE, snow water equivalent, which is how much liquid water you get if you melt down that snow. And 3 centimeters might not seem like a lot, but that's about 1/10 of our normal snow water equivalent values for seasonal snowpack at this elevation, or 14% of each storm event over average was caught in the canopy. And a cool part of the LiDAR data is that you're simultaneously mapping snow on the ground as well. So we were able to calculate there was 20% more snow depth at our aspen sites compared to our conifer sites. And you can see the evolution of snow depth at one of our sites here, where the darker colors are deeper snow and those individual dots are individual trees. And you can see that where there are more dense trees, shallower snow. So conifer structure offered nuanced results for us, but essentially those vertical crown metrics for individual trees only explained 18 to 21% in the variance across interception rates. However, we could combine those together to actually explain 31% with just those vertical structure metrics. And those were the rumple index, which is the surface area of the canopy illustrated in the middle here, taper, how much the tree comes to a point vertically, and then vertical complexity index, or VCI, which is basically the evenness or diversity of tree branch spacing vertically. So we were a little surprised to see that our neighbor metrics, looking more at the horizontal scale, actually explained more variation in interception than our individual crown metrics. And again, the #1 metric that came out on top was this rumple index, except this was applied to neighboring trees. And essentially the higher surface area, larger neighboring trees limited interception of smaller trees that might be in the middle of that stand. And we wondered why this was, but our hypothesis was supported by the literature that bigger trees actually limit wind speed, which is going to limit interception because you're essentially changing the horizontal trajectory of a falling snowflake, where if it's blowing sideways, it has more surface area to interact with than if it's falling straight down. But with both of these, we could only explain about 40% of the variation in our data set. And we were a bit bummed about that. So we decided to subset our results and only look at isolated trees that didn't have neighbors, were not in the middle of tree stands. And when we did, we got a much higher R-squared value of 0.6. And again, vertical complexity index, how diverse the canopy spacing is vertically, came out as the best predictor. So this is telling us that there's a lot more to find out about the impacts of neighboring trees on interception. And this is the result of our model, for our statistical model for all our results, that one that could explain 40% of our results. And you can see that we've got the trend pretty dialed, but we're falling off of that 1-to-1 line a bit. So definitely some work to do there. We saw conflicting trends across different structural metrics when we were thinking about those vertical canopy structures. But what was reassuring is that across those neighbor metrics, we actually saw consistent trends across species. So just to wrap this up real quick here, aspen trees intercepted a lot more snow and therefore we can expect a deeper snowpack on the ground and more snow water equivalent in that aspen under that aspen canopy. However, aspen trees have less shading, so that snow is likely to melt out faster. And to think about this in terms of where our forests are going, we know that aspen can be that successional species that comes in after lodgepole pine disturbance. So that might be a bump in how much water we have in our snowpack. But we know that spruce fir can also be a successional species after lodgepole pine, which would be a transition in the other direction to having less snow on the ground. And just to fully wrap things up here, we saw differences across aspen and conifer, across different conifer species. Structural trends were influenced by conifer species. There's going to be less snow water resources in conifer forests compared to aspen. And those spruce fir climax states after succession, we can expect there to be less SWE that makes it to the ground as well. And then just to note on this really fast, we don't have a remote sensing mechanism that is able to look at species ID of individual trees across a big scale. So that's kind of a big deal because without species, our results were a bit nuanced, and we would like to work towards structural predictors that don't need species so that we could expand our results across the whole watershed. So yeah, thanks. I'll pass it on to our next presenter.
All right. Thank you, Curtis. We don't really have any time for questions right now, but I'll save up a couple for you for the question Q&A following the panel presentation. And amazing study.
Cool.
And good job skiing while you studied.
Thanks.
Okay, so for my MEM project, I have been working with the Hemlock Restoration Initiative here in Asheville, North Carolina. So for some background on my project, the Hemlock Restoration Initiative is a program of a larger nonprofit called WNC Communities. HRI aims to restore and protect the existing hemlocks on the Western North Carolina landscape. They primarily work with two species of hemlocks, which are the only two native hemlocks here in Appalachia. There's the Carolina hemlock and the Eastern hemlock. For the purpose of my project, I'm just going to be talking about Eastern hemlock, or Tsuga canadensis. This is a tree that provides a suite of ecosystem functions. It's super widespread in its distribution. It grows all the way up in Nova Scotia, southern Canada, and it spans all the way down to southern Georgia, encompassing a massive part of the Appalachian region. Eastern hemlocks are what you call a foundation species, which means that they provide structure and habitat for wildlife, such as birds and fish. They also aid in nutrient cycling. They slow down the nitrogen cycle. They typically will grow along these lower elevation areas where there's streams and rivers and sometimes acidic coves. They're often found at lower elevations where there's more of an abundance of water. And they're evergreens, and they're providing an immense amount of shade over the ground and over the rivers that they're growing along. And this is what allows the rivers to stay cold, allowing the rivers to hold more dissolved oxygen for fish and macroinvertebrates and salamanders and whatnot. And they also, with the shade, they're also able to slow down the decomposition of leaves and organic matter. And this is what slows down the influx of mineral nutrients getting into our waterways and potentially causing algal blooms. They also aid in stormwater retention when they become photosynthetically active, which is in the springtime. They sequester a lot of water, which can reduce catastrophic floods. So what has essentially been going on with these trees is an invasive insect was accidentally introduced in the early 1900s, around 1950, on nursery stock. The insect is called the hemlock woolly adelgid. This adelgid is in the class of insects called hemipterans. They have piercing and sucking mouth parts. And essentially what the adelgid does is it inserts its stylet, which is its mouth part, at the base of these needles of these trees, and they siphon nutrients in the form of mineral nutrients, carbohydrates, and water. And in response, these trees just wall off the infected tissue, and they kind of just these trees essentially just kill themselves due to this hypersensitive response. And as far as management goes, the Hemlock Restoration Initiative carries out chemical control. There's two forms of chemicals that they apply on state and federal lands that can, based off of what chemical you use, these chemicals can provide protection for these trees for up to 7 years, which is pretty solid. As far as biological and mechanical control methods go, I've kind of integrated these two management techniques into my project, and I'll talk about those in the coming slides. So this is just a map that I wanted to include. This is the current distribution of hemlock woolly adelgid in 2023. This is extremely impressive because the adelgids are very sessile. They don't move a lot on their own accord. They rely on birds and wind for their dispersal. And you can see they're in more than 50% of the Appalachian region. And so at this point, as far as management goes, it's really a matter of suppression versus eradication. So getting into the biological control, which has kind of been, this part of things has been integrated into my project, which I'll get into in a couple slides. But there is a suite of biological control agents that have been introduced to Western North Carolina and other parts of Appalachia to reduce the effects of hemlock woolly adelgid on these trees. The two that I've really been looking for my project as part of my site assessments here in Western North Carolina is the Laricobius nigrinus, which is a beetle of Laricobius that was introduced from the Pacific Northwest, where there's a native lineage of hemlock woolly adelgid. And then the second one is the Laricobius osicensis, which was introduced from the southern Japan region. And both of these insects in the same genus are host-specific on the hemlock woolly adelgid. They feed on nothing else except for the adelgid. These beetles are synced up to the life cycle of the adelgid. You can see in this chart above the beetle image. The hemlock woolly adelgid life cycle is pretty atypical compared to other insects within the insect kingdom. They have this it's called the summer estivation period, where they're essentially dormant through the hot part of the season. And then as it starts to cool down around October, November, December, they're entering their adult stage. And throughout that adult stage, they're putting on this waxy wool substance around their bodies, which they will ultimately use upon February and March to oviposit their eggs inside this waxy wool, which essentially provides like protection against predators, a little bit of insulation it provides. And throughout the development of the hemlock woolly adelgid, these Laricobius beetles are actively feeding on the adelgids. So moving on here, there has been research done by the United States Forest Service Southern Research Station here in Asheville. Essentially what they did was they set up silvicultural plots where they mechanically released surrounding composition, such as broadleaf deciduous trees, in an effort to remove competition from trees that they have found on federal and state lands. And this is all part of an adaptive management plan to see if these quote unquote insectaries can work in rearing biological control agent. What they ended up finding on some of these plots was that once they exposed these eastern hemlocks to an abundance of sunlight from releasing trees in the surrounding area, these hemlocks were able to put on a lot more new growth. They became a lot more photosynthetically active. And adelgids really only feed on the new growth tissue of these trees. And so the idea is that these silviculturally managed plots in the forest that have been opened up, if they give rise to more new growth, ultimately they could give rise to more hemlock woolly adelgid, which has already been kind of seen by eye by the researchers at the Southern Research Station. And then in turn, these sites could end up being really good rearing opportunities for biological control agents such as the Laricobius beetles and future biological control agents that they might introduce in the coming years. So knowing this, having this preliminary knowledge of this research, my work started, my project essentially started here I created an initial assessment that we called that I called a checklist, which is essentially used to assess sites across Western North Carolina that could be suitable for the silvicultural management or these enhanced insectaries. And so on this checklist, I just asked myself some preliminary questions that might pose pertinent for these sites turning into insectaries. And so some of the questions that I asked myself were, I wanted to know how many trees were at these sites. I wanted to ensure that there was a lot of trees so that if management was conducted on these sites, the management would be worthwhile. There would be enough trees for there to be an eventual boom of hemlock woolly adelgid at these sites, and then in turn, having a lot of trees that provides a whole lot more real estate for both the hemlock woolly adelgid and the Lyricobus beetles. So ultimately, the goal here is to create a threshold of adelgid that the trees can withstand without dying, and enhancing these sites, creating these insectaries, giving these sites the ability to harbor more biological control agents is kind of the ultimate goal here. So other questions I asked on this checklist was if there was living overstory hemlocks, and this might be pertinent because if there's surrounding older growth hemlocks, there could potentially be hemlock woolly adelgid way up in the tree. It also could be refugia for beetles. And so a lot of these questions were just preliminary questions that I asked myself, and I just wanted to make sure that each of these checklist questions would be answered across the prescription that I ended up creating in the coming slides, so that each question is comparable across each site that I surveyed. And so from the checklist, I ended up creating a prescription plan, which ultimately was a template that ultimately can be used by land managers across the region that will aid in creating these enhanced insectaries. And so to go along with the prescription form, I created this supportive documentation guide, which essentially is just a step-by-step process that I will give to land managers for them to use when they're filling out the prescription form. The prescription form has jargon that not everybody might be able to understand, and so this was just a guide that land managers can use when assessing the sites. And so this prescription form that I created has a list of management recommendations, site characteristics that can be compared across all of the prescriptions that are filled out for creating enhanced insecticides. And on this guide, I created a protocol for looking at adelgid density. I created a description on hemlock woolly adelgid predators, like how to assess for that, how to assess for describing the regeneration conditions of the site. And so then it really just came down to assessing the sites. And most of my sites looked very similar to this picture here on the left. So essentially, these trees have this unique habit. The eastern hemlocks have this unique habit of regenerating and harboring adelgid pretty well in the understory without dying. These cluster of trees were able to put on a lot of new growth. This larger tree to the left here that has no live lower branches, that's actually an eastern hemlock. And the adelgids, when they infest a tree, they typically will kill the tree from bottom to the top. And so the tree ends up just calling the branches that are not really getting a lot of sunlight. And so they end up being the lower branches here. And so a lot of the sites didn't really include trees of larger status, because this is kind of just what you see out here when you do have an adelgid infestation. So these littler trees pose to be better insectary trees, because you can go into the site and you can look for hemlock woolly adelgid because they're right in front of you. There's living tissue right there for you to look at. You can look for biological control agents such as Lyricobus beetles. And then in the middle here is just a photo of me and my coworkers looking for biological control agents, looking for Laricobius beetles. We use this method called beat sheeting. And then on the right here, this is what I would call a high density of hemlock woody adelgid. You can see all those ovisacs at the base of those needles there. And so going along with the prescription form that I created, I also, so I ended up filling out 6 total prescriptions for potential insectary sites across Headwater State Forest and DuPont State Recreational Forest here in Western North Carolina. And I created maps for each of these sites that outline unique polygons of patches of hemlocks, particularly regenerating hemlocks. And then to go along with those polygons and patches, I created just little descriptions of what the land manager is going to see, what he or she should expect when going into these sites. And so you can see in my key here, there's just little descriptions of, you know, what the area looks like, what sort of management is going to need to be done to open up that area to more sunlight for these trees to put on more new growth. That's pretty much it for my project. I want to thank Tom Green and Margot Walston with the Hemlock Restoration Initiative. They have been instrumental in helping me with this insectaries project. I so appreciate their expertise. They were wonderful people to work with. The North Carolina Forest Service, I thoroughly appreciate these folks as they allowed me to conduct these site assessments on some of their land. Of course, AmeriCorps Project Conserve, thank you so much for providing me money and livelihood and a tremendous cohort that I got to know over the course of 9 months. And then last but not least, Brooks Intel, thank you so much for being a wonderful MEM advisor to me. You've taught me so much and instilled so much confidence in myself over the past 2 years, so I really appreciate it. Thank you. And these are just some final photos.
All right. Thanks. Yeah.
Hey there, Dr. Coop. Thanks, everybody. Am I taking questions now or later?
Landon.
I can hear you. There's just a little bit of an echo.
Yeah, we know. Questions later, Landon.
Hello. This is not my conclusions. Okay, hi, I'm Tina. I looked at Gamble Oak Ecology and Management in the Uncompahgre Valley, characterizing communities and developing baseline data to test intervention effectiveness. So Gamble Oak is a woody deciduous shrub native to the southwestern United States. It occupies 3.5 million hectares. And it provides key habitat for a variety of game species, such as deer and elk, as well as a habitat for Colorado state butterfly, which is the Colorado blue hair streak, and a bunch of different birds. It displays a wide variety of growth forms across its range, from being a little shrub that we're probably most familiar with. If you drive out towards Montrose, you see these little bushy dudes. Those are the oaks. But sometimes they're trees, which is pretty exciting. And they're able to re-sprout via these underground root structures. So when there's pretty catastrophic disturbance, such as extreme fire, they're able to come back pretty fast. One of the fastest of all the woody plants. So this project came about thanks to the Baldy Mountain Landscape Resiliency and Habitat Improvement Project, which the GMUG Forest Service, NFF, Mullins Ranch, and the Uncompadre BLM and some other private landowners all got together and wanted to treat Gamble Oak to reduce fuels and improve game habitat on Baldy Mountain in Uray County, Colorado. And all of these treatments are going to be done over the next couple of years, and they started last summer. So there's two goals of my study, which is one, to develop an experimental design so that we can test the intervention effectiveness. So what are these treatments actually doing and how effective are they? And then also to characterize that variation in oak in this area. So to develop experimental design, I had 4 treatment types. There's control, which is that blue band on the outside, and it's a 100-meter wide band with a 25-meter buffer from the other treatment types. And the other treatment types are mastication only, seen in that aqua, and then mastication and fire, which occurs both in the orange and that pinkish color, and then mastication, fire, and herbicide, which is only going to occur in the orange areas that show oak encroachment into meadow type systems. And so we stratified 30 sample sites into each of the main 3 treatment types, which is mastication only, mastication, fire, and control, and then 10 sites in that oak encroachment area where herbicide might occur. And all pre-treatment data was collected over last summer. So what did the sampling look like? So we went out and we set up these plots. They look a little bit like a peace sign. Within the circle, that is a 0.01 hectare circle. And within there, we measured all of the stems at DBH, which is diameter breast height. So right here. And we measured all of the stems. And if they were too small, so smaller than 2.5 centimeters in diameter, we just counted those up. And within each of those 1/3 sections of that circle, we took a borer and cored the largest tree. But if the largest tree was too small to core, because they are little oaks, we took a proxy tree from outside and we got a cookie. So we aged those. And then on each of these transects, these lines coming out from the center, which go in the 0, 120, and 240 directions, we measured all of the vegetation at every half meter. So we use the line point intercept method. So you drop a little point, and every plant that hits that point below DBH, we identified to species. So that's 60 points per plot. And then we measured fuels using the Brown's planar method for 1, 10, 100, and 1,000-hour fuels. And that just refers to the size of the stick that's on the ground, with 1,000-hour being the largest. And then we also measured litter and duff, which is that leaves on the ground at every half meter along those same 3 transects. And then we also did abiotic plot characteristics, including slope, aspect, landform, and shape. And we took soil samples at the very end of each of these 3 transects, which we analyzed for texture and soil organic matter. So the second goal of my study was to characterize the variation in Gamble oak systems. So we identified 4 different growth classes of Gamble oak. And here's some pictures. In the upper left, that is the sparse shrub, which characteristically has the smallest stems and the fewest stems per hectare. And then we have the sparse savanna, which have larger stems and not very many of them in a site. And the dense savanna has large stems and a lot of them. And then the dense shrub, which is this very scary little patch down at the lower right, and that has tons of stems, and they're not very big and they're not very fun to walk through. So we looked at stand characteristics for these 4 growth classes. So we looked at stem basal area, which we calculated using that measured diameter breast height. Then we have Gamble oak canopy cover, Gamble oak understory cover, and the stems per hectare. So the highest stem basal area was found in that dense savanna. Remember, it has lots of large stems. So that makes sense. And the least was in that sparse shrub, tons of little, or not very many little stems. And then we have canopy cover was also highest in that dense savanna. And the other three were about the same. And then for Gamble oak understory cover, that was highest in both of the shrub type growth forms, and lowest in the savanna type growth forms, which makes sense as the shrubs aren't growing that tall. So there's tons of those little sticks and stems near the base. And then for stems per hectare, that was highest in both of the dense growth forms, with dense shrub being the highest, as there was bajillions of stems everywhere. So I also looked at stand age classes. The oldest tree we sampled was 244 years old, which is crazy because these little oaky dudes. And the largest trees often did have heart rot. So when we went to take a sample, we actually weren't able to take it because it was rotten on the inside. So there probably were trees over that 244-year-old mark that we just weren't able to sample. And then because if you look at this graph, a lot of these trees are over 100 years old, which indicates there hasn't been stand replacing disturbance in these areas for over 100 years. And the older, larger stems belong to that savanna, that sparse savanna growth form. So those areas haven't seen any crazy disturbance in a really long time. Something interesting to note is the sparse shrub growth form tended to have quite small stems, but they were actually pretty old, nearing that 100-year mark. So I performed a non-metric multidimensional scaling ordination, which basically takes all of my species cover on both the understory and overstory and plots each species, and then displays the communities of each sampled site in the simplest fashion. So each of these points is one sample site, and the closer 2 points are to each other, the more similar those communities. The large distance means those two sites have extremely different vegetation communities. And something you should note is that sparse savanna growth form does tend to kind of group together in the lower right zone, whereas that dense shrub is kind of grouped together in that upper left, and the dense savanna and sparse shrub are kind of mixed in throughout. So I overlaid abiotic factors on top of these NMS ordination plots. And community variation is pretty highly correlated to elevation and soils, as you can see here. In that elevation graph, the sparse savanna occupies those higher elevations, whereas the dense shrub is found at the lower elevations, shown in that bright green. And then if you look at sand and clay, more coarse soils were most associated with that sparse savanna growth form and least associated with the dense shrub. And reversed is the dense shrub had more fine soils and the sparse savanna had more coarse soils. And this can likely be attributed to that elevational change too. You know, mountains degrade from the top down, so those smaller ones are down at the bottom. And then soil organic matter, the highest percent was most correlated with that sparse savanna. And that makes sense because these are deciduous trees. They drop their leaves every year, and these stands have been established for an extremely long time. So over the past 100 or so years, all of those leaves are in the soil, and they're showing up as that soil organic matter. So what can we conclude? Oak community structure and composition varies with abiotic factors and stand age. And so each of these growth forms displays variation along those lines, as well as within their communities. And treatments will affect each growth form class differently, with the dense shrub responding most quickly to treatments, as there's tons of those little stems and they'll quickly regenerate. With that dense savanna having been established for a super long time, severe like disturbance will totally knock it back and it won't exist anymore, at least for 100 or so years. And I recommend resurveying sites after 1 to 2 years and 8 to 15 years after treatments are done to see how quickly they are responding and then the long-term effects on community composition. Thank you to all of these people, especially all of my committee members and everybody that helped me and my field technicians. And a huge shout out to Dustin Mullins, who let me stay in this very, very, very cool little house for the entire summer. So yeah.
All right. Thanks, Tina. I think what we'll do is just in the efforts to keep things kind of on track time-wise, we'll just move on to the next presentation by Jack and then get some questions out in front of everybody at the end of Jack's presentation. So
Sounds good. Thank you, Coop. All right. Good morning, everybody. We're going to talk about sagebrush and a changing climate. Real quick, again, my name's Jack. Super into plants, got into that in my last few years. My undergrad at UC Santa Barbara, and since then I've been working a bunch of different survey gigs with different federal agencies, research institutions, collegiate labs. And a lot of the questions we are looking at is how are these landscapes changing over time? The long-term monitoring projects going back year after year after year, looking at what's there. So getting to Western, I'm looking at sagebrush around me and I want to know, how is this changing? You might ask, why should we care? It doesn't really have the charisma as a lot of animals or even like a redwood or something like that, a tree. It's a little scrubby shrubland. We've actually lost about half of the sagebrush biome in the American West. It used to be 60 million hectares. Now it's about half that. What remains is pretty degraded, fractured by roads, canals, urban development, resource extraction. It's being hurt by cattle grazing. There's biotic invasions of cheatgrass, of pinyon juniper. But you don't really see these as much, in part because the biome is so massive and undervalued. You don't really look at it that often. But these changes are happening. And there's a lot of interesting questions to be asked here. Sagebrush is also home to a lot of obligate species, including our own Gunnison sage grouse, the threatened greater sage grouse. We got the endemic Gunnison milkvetch, as well as a great place to recreate, as we all know. There's a study done in 2015 that was looking at the number of studies between 2010 and 2015 that incorporated drought and heat waves into plant mortality studies. A lot of them took in drought. About 1% incorporated this hotter drought, this combination of heat and drought. And I'm also looking at sagebrush seedlings. Sagebrush have a type 3 survivorship curve, meaning most of the mortality occurs when they're very young. You can see on the graph on the top right, once they're more established, they're a lot more hardy. But if they're going to die, it's likely when they're seedlings. So my objective was to run a crossed experiment in the greenhouses and the environmental growth chambers here at Western, testing 2 different subspecies of sagebrush to 2 tiers of heat and drought conditions. And we'll get into that more in a minute. So these are the players we're looking at. Artemisia tridentata is our big sagebrush here. There's a lot of different species of sage, but tridentata is the main one in the valley. That being said, there's also subspecies of tridentata. So we're going to look at mountain big sagebrush, which is Artemisia tridentata bassiana on the right column there, and Wyomingensis, which is Wyoming big sage on the column on the left. I know there's a lot of text there. In a nutshell, what we're supposed to take away from this is the Wyomingensis occupies typically lower elevations relatively. Of course, we're still a high valley, but lower elevations, less precipitation, shallower root system. And you've got small morphological characteristic differences in, say, the canopy, the inflorescence stalks coming through, the color. Mountain sagebrush, a little bit more mesic sites, a little more rain, deeper roots, a little denser. That being said, they're really hard to tell apart. I've spent a lot of time IDing plants, and it's very tough to tell sagebrush apart, especially because they hybridize. So some of those differences that I mentioned, it might be somewhere in the middle because it might not be one or the other, it's both. But different methods include looking at morphology. That's tough, especially when they're, a couple inches tall, they don't have an inflorescence, et cetera, et cetera. Black light is also used to differentiate. Different coumarin counts in the sagebrush will fluoresce blue when put in water or alcohol and exposed to a black light. Mountain big sagebrush fluoresces bright blue. Wyoming big sagebrush fluoresces dull blue, which is not quantitative at all. So that's only so helpful. They differ in their ploidy level, the number of chromosomes. The Wyomingensis is a tetraploid. The mountain big sagebrush is mostly diploid, but can also be tetraploid. But there's this really interesting paper in rangeland ecology and management that uses spectrophotometry to identify quantitatively the difference between these two subspecies, which we'll get into in a moment. My field work this summer was up at Cabin Creek, just east of town, about 10 minutes away from Gunny. And I wanted to find an elevational gradient. So I put sites about 400, 500 vertical feet apart, about 10 to 13% slope, roughly 150-degree aspect. And I collected adult tissue samples from all these sagebrush at these sites to run this spectrophotometer method to identify their subspecies, basically trying to establish this same gradient that we expect. At each of these sites, there is also a data logger inside a PVC shield, which has been posted about 3 inches above the soil. That takes temperature every 20 minutes. And then I went up every 2 weeks and recorded soil moisture with a handheld soil probe. My lab work, I took my seedlings that were grown by the Colorado State Forest Service in Fort Collins, brought them back down to Gunnison, acclimated them here to the greenhouse, described 12 groups. We're looking at 2 control groups, 2 drought groups, and then multiple combined stressor groups and just heat wave groups. There's going to be, for the drought, I did 5 weeks of water withholding. So this was measured with another soil moisture probe. I aimed at about 0.05 volumetric water content of the soil of these seedlings that are going through the drought. And that was maintained as needed. I'd monitor, add more water, let them dry out, add more water if needed. Our control was 0.25 volumetric water content. That was determined by watering the soil to capacity and letting it dry for an hour. Our heat treatments is 1 week of extreme heat. A heat wave is typically defined as over 3 days, consecutive days of this extreme heat. Literature suggested 10 degrees higher than the hottest week of the summer. So we determined 35 degrees and 40 degrees. I did 2 different heat treatments, and that's about 95 degrees Fahrenheit and 104. So it's hot. And then for the combined stressors, the last week of the drought, that 5th week, they also got the heat wave. Nice little sagebrush up top right there. That one did have 2 plants growing it. So I pulled the one that was less dominant, but that didn't occur that much. Variables that I measured: plant height, stem diameter, leaf area, root length, discoloration, mortality, and then I calculated growth, relative growth rate, specific leaf area, which is the leaf area divided by the dry weight, and the height base root to shoot ratio to see if these were affected by the treatments or if they affected mortality. Right there is the spectrophotometry graph in which the absorbance values revealed that site 1, which are our highest elevation, is going to be that purple line. That is Bassiana, Mountain Big Sagebrush, according to the Richardson paper. And our sites 4 and 5 is going to be the Wyoming Big Sagebrush. Those are our low elevation sites. And the ones in between, sites 3 and 4, are likely hybrids due to these absorbance values within 340 to 350 nanometer wavelength. I know it's a lot going on there, but basically now we know what we're looking at. Results from the fieldwork did show this temperature and soil moisture gradient across elevation, which we also expected. Wasn't a huge range, but we can see on the left here that the higher elevation sites had more moist soil, drier low down, as well as it was a little bit cooler higher up and hotter lower. That is my PVC shield on the top right there that has the temperature logger in it. These are recording again every 20 minutes. The graph here is the daily maximum. The red bars are going to be my 35 degrees Celsius and 40 degrees Celsius heat waves that I measured in my experiment. This is showing that this did occur on the ground over the summer. It was a surprisingly hot summer. Honestly, a lot hotter on the ground, it seems, than maybe ambient temperature in Gunnison. So those are all our different sites. They all experienced over 7 days of a max temp over 35. Most of them experienced over 7 days of a max temp of 40. Some plots of our lab work. There wasn't that much difference between pre and post on most of these, in part because the measurements were about 9 weeks apart, so there wasn't that much time for the plants to grow, so there wasn't that much recorded growth, or therefore relative growth rate. Roots kind of tapped out in the bottom of the plug, so they didn't get very far there. There was a significant difference in specific leaf area of pre-treatment data between the two collection site locations. And I say collection site locations because we don't know for certain that it's Wyomingensis and Bassiana. We do for the field sites, but for the experimental seedlings, we're going to call them low and high elevation. The meat of the project really looks at mortality, because we're interested in sort of the implications that this Wyomingensis that has shown in other studies more drought resistance to cavitation and other characteristics there. We expect them to do a little bit better in a changing climate. The data does reflect that. Our green bars in the lower right is the survivorship of the low elevation sage. Gray bars are the high elevation sage. The main takeaways here, the combined stressors decimated the seedlings. The low elevation, not as affected by heat as the high elevation. And drought was better at taking down both regardless of the elevation. And we use a generalized linear model to map seedling mortality to these different treatment types. Implications and further studies, there's definitely a lot more questions to be asked. But if we're thinking about community change, range shifts, looking at recruitment in Cabin Creek on the ground, it's possible that the lower survivorship of the high elevation, if it also has less recruitment, maybe that hybrid zone increases upwards, or this lower elevation sage type moves up. In terms of restoration, you could think about planting more of this low elevation sage in your seed sources strictly from that, knowing that in a changing climate where these heat waves and drought are going to become more common, it'll have to be a little bit hardier. Be curious too, looking at ploidy effects. There have been studies showing difference in survivorship or hardiness with diploid versus tetraploid versions of these subspecies. Anywho, I'd like to thank my committee, Dr. Coop, Dr. Bingham, Dr. Carroll, as well as Brian Stevens at the BLM for providing the sagebrush seedlings, the nursery in Fort Collins for growing them out, as well as Andres Villa for helping me in the field. Thank you, guys.
All right. excellent work, you all, and I really commend you on the technically challenging studies that you all embarked on, and what you were able to learn in the process of conducting this work. So we were supposed to wrap this up at about 10:30. Maybe we'll bump a little over that since we got off to a little slow start. But this would be a chance to ask the questions for the panelists. And so I'll start with Curtis, and I'm trying to sort of cherry pick a question that I think will be most interesting or challenging out there for you. So let's go with this one, though. Do hydrologists prefer management that promotes quick melting to avoid sublimation, or keeping water in the forests and melting at a slower rate?
Yeah, I think historically it's been the former, because we know the faster we melt snow, the more efficient it runs off to the river. But there is this conflicting trend in a new climate where in a warmer world, we expect snow to melt slower, which is counterintuitive. But if the melt season starts earlier, typically peak snowpack for us here is early April. But if that bumps earlier and snow is melting earlier, our days are less long, so there's less radiation to melt that snow quickly. So that can actually lower runoff efficiency. So there's a little bit of a caveat there, but usually faster is better to get that water in the streams.
Should we just torch all the conifer forests and turn them into aspens?
Yes, no, let's stop short of that, but let's definitely think about the intersection of healthy forests that probably aren't packed in as tight as they can be, and how that could benefit hydrology in our watersheds.
Awesome. Okay. So I'm going to ask a question for Landon, and then if he responds, Jillian will read his answer rather than the cool special feedback effects that I was hoping for. So the question is, Landon, if you're still there, do you think it's possible to implement insectaries to make a landscape scale impact? Or are these treatments more useful in conserving small stands of hemlock? Should I wait? Or we'll give you a chance to respond. Maybe should we jump over to another question in the meantime? Okay. So Tina, awesome plots for the abiotic factors. Are there other factors you didn't study that you anticipate influencing stand structure and composition?
I'm sure there are other things. I think like especially something that would be interesting to look at would be climate and soil moisture, like in each of those plots, because we didn't find any like significance with slope or aspect on any of my NMS ordinations, which is weird. So I wonder if a better proxy would be like soil moisture and like availability to those woody species, because that varies with soil texture, slope, and aspect. So that might be a better way of going about that, and maybe you'd see some significance there. But yeah, there you go.
Okay, soil moisture.
Yeah.
Somehow we're going to be integrating all of your forest studies here at some point. Okay, do you have an answer from? Okay, too problematic. That's a great answer, by the way. It's just too problematic. Okay, Jack, what did the high range of size of the sagebrush look like in the pre-industrial timeline, and how has this maybe changed within the modern age of increasing climate change? The question is, what did the high range of size of the sagebrush look like? just speculate on differences between historical and contemporary distributions of sagebrush.
I'm imagining they're talking about the range and not the size of an individual plant. I'm also guessing this is talking about sort of just the degradation of the landscape as a whole. The question was, why is that? Why the change?
Just speculate.
Speculate. Development a lot. We're here, we affect our landscape, we build things, we extract things. And we've done it very well. I think not many of our habitats are kind of immune to that, sagebrush included. So
Do you think sagebrush is well poised to shift upward in elevation under climate change, or should we be giving it a little boost or trying to slow that down?
I think that is a excellent question. Looking at applied management, making those decisions, it couldn't hurt to give it the boost. I think right now you kind of have to pick and choose your targets. We only have so much time and so much money. I would say keep an eye on it for sure. Keep those options in the toolbox. But as of right now, it seems if it's going to happen, it'll probably happen on its own. And the lower elevation sage does seem like it's in a good spot to kind of keep thriving.
Okay. Maybe I'll ask a question for all of you. What do you think was the most challenging part of your research?
I'll kick this one off. A lot of it for sure, unexpectedly, but then you're in it and everything's kind of tougher than you might think at first. But keeping everything level within an experimental setting, like making sure that all my soil moistures were dialed. There was a lot of specificity, a lot of constants that I had to keep very accurate. And I had maybe 550 seedlings. So it was definitely a lot of checking in on them and making sure that things were where I needed them to be so that the results could be useful.
Yeah, I'd say for my project, it was probably dealing with just how noisy the data is. I think that probably would go for all of us. There's this creative aspect to doing ecological research where you need to be able to filter what you're seeing based on what's noise, but what's actually a signal you can trust and create like a supported scientific story for. So I think that creative element was the hardest for me.
Have you ever walked through oak? That was the hardest part.
Okay, we do have an answer from Landon here, but I'll just reiterate my appreciation of how difficult the scientific endeavor is and the many, many pitfalls and challenges that come up in this journey. And also just commend you all again on the work you've done to try and find the signal through the noise and the scrubby shrubberies. Okay, so here is the answer from Landon, and then I think we'll wrap it up. But the idea, remember the question was, is this can this be a landscape scale, or is it just a sort of local stand scale intervention? And the answer he wrote is the idea of creating hemlock insectaries is to create more suitable habitat for the biological agents like the beetles. For that reason, implementation is centered around labs that have rearing capacity for said beetles. And not every location in the Appalachian region has the resources to rear control agents. So constraint on the widespread utilization of these approaches. Okay, how about just a huge round of applause for all of our panelists, including Landon out there in Zoom land. Thank you all very much, and we'll see you guys back here. The next session starts in 10 minutes. You get a little extra time. Well, Jillian says 5, Micah says 10. I'm just telling you, you can pick and choose which like